It's time to experience something glorious. Unacademy Combat. Compete, crack, conquer.
A challenging GATE contest engineered to give you an experience like none other.
Where you put your knowledge to test
and battle it out with the best.
To bring out the best in you, Unacademy Combat is the most competitive, gamified contest for GATE till date, with the best of the questions by best educators.
with detailed video solutions from top educators right after each contest.
Combat live with peers to get real-time rankings and win big.
Participate in every contest to improve your ratings.
Challenging contests every fortnight or alternate Sunday. Live ranking after every question. Big rewards for top rankers. Your passion to crack GATE deserves this. Your hard work towards your dream deserves this. Fuel your inner fire for the ultimate GATE challenge. Unacademy Combat. Register now.
Hello everyone, good evening to all. So good evening Vamshi Krishna, Harsh, good evening, Subhani, good evening. Guys, let's share the session to reach the maximum. Share the session guys. The live count should be increased. Share the session guys. Good evening everyone. Krishna, good evening. Share the session guys. Am I audible guys? Am I audible? Am I audible guys? Am I audible guys? Pratap Singh, good evening. Yes, we are audible. So in this session, hello everyone, welcome to Unacademy. Welcome to GATE Conqueror. So in this session, we are going to discuss about switching concepts in power electronics. So in this session, we are going to cover, what is the need of switching in power electronics, how we can place the switch, and the properties, losses and types of the switches. So let me introduce myself. I am Sathish Kumar Kesireddy. I got the AR 18 and AR 286. So I had a 10 plus years of teaching experience. So I did my MTech in Power Electronics in NIT Tiruchi. So I was ex-BHL employee. So I was expertise in the subjects of Power Electronics, Power Systems and Network Theory. So if you use the KSK10 as a code, so you'll get the 10% in Unacademy Plus subscription. So now, so these are the special class features. Special classes are nothing but, so these are the free classes available in the Unacademy Learner app. So if you download the Unacademy Learner app, there you can find the special classes. So these are all the features, interactive live classes. So the classes are interactive, educator and learners are interactive. So polls for the learners are created. You should respond to the polls for better understanding. So never miss a calls. So you'll get the notification. So guys, you'll get the notification if you follow the faculty, your favorite faculty. When they have scheduled the class, you'll get notified. So now lecture notes can be downloaded. So the lecture notes also can be downloaded in Unacademy Learner app. So unlike YouTube, so you can watch anytime, anywhere. So that because it's an online platform, you can watch anytime, anywhere. So we have two subscriptions. One is Plus subscription and other one is the Iconic subscription. In Plus subscription, so we have live classes. In Plus subscription, we have live classes, crash courses, weekly test and doubt solving. So the classes are in both English and Hindi. So in Iconic subscription, so in addition to all these features, we have the personalized coach. Personal coach will be allotted. So study planner is there. Study booster sessions will be conducted. So personalized test analysis is there. Preparatory study material will be also available in the Iconic subscription. So now let us see the fee structures. So here you can opt for the 12 months, 18 months and 24 months. So these are all the fee structures for the 12 months, 18 months and 24 months. These are all the fee structures. So if you cannot able to bear the total amount, so you can opt for the no cost EMI also. Now, so these are all the fee structure for the Iconic subscription. So for the 12 months, 18 months and 24 months. So with the inclusion of 10%. So these are all the amount. Here also, if you cannot able to bear the total amount, you can opt for the no cost EMI. Now, so after using the KSK10, so you will get the 10% discount. After using the KSK10, so you'll get the 10% discount. After 10% discount, this is the amount. So for the 12 months, 18 months and 24 months. Similarly for Iconic subscription, so we have the 12 months and 18 months, 24 months subscription. These are all the fee structures. So now, so this is the offer alert. So this is the offer alert. If you subscribe for the 12 months, you will get the plus additional 2 months subscription. So plus 3 months subscription for SSC, JE and State AE exams. So if you opt for the 24 months, you will get additional plus 4 months subscription. So the plus 6 months for the SSC, JE and State AE exams will be added. So if you opt for this offer, so you will save these much amounts for 12 months and 24 months respectively. So this is the accelerated Arohan batch which was started at 18th August. So by the best educator in the Unacademy. So these are all the 2 subjects started, control systems and EMF theory. Similarly, so this is the accelerated Arohan batch for the ECE. So the 2 batches will be control systems and EMF theory, which is also started at 18th August. So this is most interesting. So Bugs Bounty. If you find any inappropriate content in the video, so you can report to the Unacademy. There you can get the reward from the Unacademy. So if you want to follow my special classes, so you should have the Sathish Gate. So at the rate Sathish Gate, this URL you need to be used. Whenever I schedule the special classes, you will get notified. So now let us enter into the session. So let us enter into the session. So now we will see what is switching concepts. So the switching concepts in the power electronics. So when you observe that in the intro itself, I have said that. So the power converter circuit is the major in the power electronics circuit. So the power converter is the major element or most significance. Power converter has most significance in the power electronics schematic diagram, right? So which is built with the switches and energy storage elements. Switches and energy storage elements such as inductance and capacitance. So these switches are power semiconductor devices. These switches are power semiconductor devices. Again, these switches are divided into bipolar and unipolar devices. In a bipolar devices or unipolar devices, we have the power diode, power transistor, so power transistor, power MOSFET, power IGBT. So these are all the switches in the bipolar and unipolar switches. Similarly, so we have other classification also. They are thyristors. So that in the thyristor family, we have the SCR, silicon controlled rectifier. So we have the GTO, gate turn off thyristor, triac, we have the triac. So like that, we have the different thyristor family also. So all the thyristor family we will discuss later. So at this stage, you need to understand that. So the power converter is the power converter has most significance in the power electronic system. So the power converter is built with the switches and energy storage elements. A switch is nothing but the power semiconductor device. So the power semiconductor device, these are the examples of the power semiconductor device. Let me ask you one question, guys. So what is the need of switching? What is the need of switching in the power electronics? So let me ask you one question. What is the need of switching in the power electronics? So let this session is most interactive. So answer this question. So what is the need of switching in the power electronics? So respond guys. So here, let us see what is the need of switching. So why do we require switching in the power electronics? Can anybody answer? Why do we require switching in the power electronics? Control purpose. Control. For what we can control here? So what we need to control here? Why do we require switching? So in this, for control purpose, we have the different circuits. Why we have opt for the switching? So Yashaswini, you are right. Absolutely, you are right. It is for control purpose. But so we have for the control purpose, we have different circuits. But why do we choose the switching networks in case of the power electronics? So we have different circuits that we will discuss here itself. Inverting purpose. That is also correct. But so at the basic level, if you start from the starting point, so the power converter is. So in the power electronics, the switches are used in the power converter. As you said that it controls the power. That is good. So at the basic level, so to design power converter, the most important parameter is efficiency. Important parameter is efficiency. So that is power converter is the function of efficiency. Let me give some examples. So from that examples, so you should understand that. So why the switching network is preferred in case of power electronics. Let me take the first example. So here, I will take the first example as resistive network. Let me take the resistive network here. So let me draw the resistive network. So I will draw the resistive network here. So which is also convert from one form of energy into other form of energy, right? So it has the source voltage as DC. Let it be the 48 volts. Randomly I will take the figures 48 volts. Let the output is, so let it be the 10 ohms. And here also let me keep the 10 ohms. So will it convert? So from DC input to the other DC output? Yes, it will convert. So how it will convert? So here the two resistors are connected in series. So is it act as a converter or not? It acts as a converter, like a DC to DC converter. If I can vary this resistance, I will get the variable output DC voltage. This is also acts as a converter. But what is the problem in this? So here, so this is the source resistance. Let this load resistance. Let it be the load resistance. How the output voltage can be determined here? So V naught equal to, so 48 into, that is Vs into RL divided by Rs plus RL, right? So now what is the output voltage here? So because these two are the equal resistance I kept, so that it will be the 24 volts. 24 volts. If I substitute, I will get the 24 volts. Now let me find the efficiency. So to find the efficiency, if I find the current, so some current will be flowing here. So because these two are the equal resistances, so these two are the equal resistance and they are connected in series, here also I current only flowing. Now let me find the efficiency. So what is efficiency here? So what is the efficiency of this circuit? Output power by input power. Output power by input power. Output power by input power. So if I find the efficiency, so the output power is equal to I square into RL, I square into RL. So the input power equal to I square into RS plus RL. It should supply both the resistance, right? I square into RS plus RL. RS plus RL. So I square and I square will get cancelled out. The efficiency equal to RL divided by RS plus RL. So up to here we are clear, right? So we are finding the efficiency of this circuit, that is output power by input power. So in terms of resistances. So for the 10 ohms and 10 ohms, so what is the efficiency here? If I substitute 10 and 10 here, so 10 divided by 10 plus 10, 20, which is equal to, so if I multiply with the 100, it will be the 50%. 50%. So the efficiency is less. The efficiency is less. Can we choose this converter circuit? Can we choose this converter circuit? So no, because the efficiency is less. The efficiency is less. So we cannot choose the resistive network for the power conversion. So because the efficiency is 50%. So while designing any power converter, so we should consider the main parameter is efficiency. It should be function of efficiency. So now let me take other circuit. So let me take other circuit. So as I said in the introduction, any power semiconductor device in the power electronics, it should conduct as a switch. So that is, for example, if you take the transistor, in microelectronic circuits, it can act as a amplifier also, right? It can act as a amplifier also. So here, for that amplifier, it should be operate in the active mode. So we have 3 modes, right? So what are those modes? Cutoff region, active region, as well as saturation region. For amplifier function, it should operate as a active mode. It should operate in the active mode. Now, let me take the transistor in the active mode. So now let me take the transistor circuit with active mode, with the DC source. Let me take the transistor in the active mode with the DC source. Let it be the 48 again. Let it be the 24 volts, or else I will take the 24 volts. So here I will keep the transistor here, and this transistor is operating in the active mode. This transistor is acting in the operating mode. So let it be the 6 ohms here. So let it be the 12 volts here. 12 volts here. So if I want to find the efficiency here, so it should be so how it will be? I need to find the efficiency. So the output power is, if I find the output power, so what is the output power? So 12 by 6 is the current is 2 amperes. So the output voltage is 12 volts, divided by 6, we will get the output current as 2 amperes. So now output power equal to, if I find the output power, so what happens? If I find the output power, it will be 12 into 2, 24 watts. So let me find the efficiency for this circuit also. So in this case, let the transistor is operating in the active mode. How we can find the losses across transistor? So we can find the losses also. Let me find the losses across the transistor. Let me find the losses of the transistor. So here, so the transistor power, the transistor losses will be, let it be the PT. The transistor losses will be VCE into IC, that is voltage across collector to emitter into collector current. So plus VBE into IB. This is the approximate formula for the power loss across the transistor. So we know that the base current is small when compared to the collector current. Let me assume, so this will be the 0. Let me assume it is negligible. The base current is negligible. Now let me find the VCE into IC. So what is the VCE here? Here 24 volts is there, here 12 volts is there. The VCE will be because it is operating in the active mode, the VCE will be the 12 volts. So the current flowing will be the 2 amperes. So again it will be 12 into 2, 12 into 2, so which is equal to 24 volts. So what is the input power here? So input power here, so input power equal to, so the transistor, across transistor power plus output power, so which is equal to 24 plus 24, which is the 48 watts. If I find the efficiency, so what is the efficiency here? So the efficiency will be, so 24 watts divided by 48. So which is equal to 50%. Again, I got the efficiency as 50%. Can I choose the circuit for the switching conversion? Can I choose the circuit for the power converter? So this, in this circuit, this transistor is operating in the active mode. If the transistor operates in the active mode, it will operate as a variable resistor. It will operate as a variable resistor. It will operate as a variable resistor. So that we should not operate the transistor in the active mode in case of power converters, because the efficiency is less. Because efficiency is the major parameter for the power conversion. Major parameter for the power conversion. So clear, guys? So up to here we are clear. So are you clear, guys? So clear, guys? Now let us see the switching network. So we cannot choose this network because the power loss is, the efficiency is less, which is equal to 50%. Now let us choose directly, we will choose the switching network. Let me take the switching network. So here, let me take the switching network here. So now let me take a switching network like this. I will use the direct switch here. So whether it is a transistor, IGBT or MOSFET, I am using it as a switch. So here one switch will be there. Here the switch will be there. So again it will be, let me take 24 volts here. So here the output will be the 6 ohms. 6 ohms will be here. Let it be the 6 ohms. So now if I want to find the efficiency here, so how I can find? Let us see. So let the switch is operating for the 50% on time. So because it is a switch, we can control the turn on and turn off, right? We can control the turn on and turn off. Now let us find efficiency for this circuit. What happens if you see? So if you observe this, the efficiency of the circuit, if I find if the switch is closed for the T on period, so in the total time T, let us find the output voltage first. For this circuit, let us find the output voltage. If the switch is closed, what happens? When the switch is closed in this circuit, the input voltage is equal to output voltage. So let it be the Vs. The input voltage is equal to output voltage when switch is in the closed condition. When switch is in open condition, what happens? There is no current flowing through the load resistance. The current is zero. The output voltage is also zero. So it will be the Vs. So here it will be the T on. So here it will be the T. Now from this waveform, can we find the average output voltage? We can find. So how we can find? So V naught equal to. So what is the? So Vs into T on, we need to find the area of the square. So which is the Vs is the height and T on is the width. So Vs into T on is the area of this square, right? So divided by T. So here one more term. So we are including here. So T on by T equal to duty cycle. Let it be the duty cycle D. So we are taking one term, which is the T on by T equal to duty cycle. So the T on is always less than the total time. So D is always less than 1. So from this, T on equal to D into T. So now let me replace this T on with the D into T. So where D is the duty cycle. This is how we can find the output voltage. For example, it is operating in the 50% duty cycle, D equal to 0.5. So what about the output voltage? If D equal to 0.5, so V naught equal to Vs into duty cycle. So for 24 into 0.5, so which is equal to 12 volts. So it is acting as a power converter, right? So it is acting as a DC to DC converter. So in the output, by varying the duty cycle, we can get the So we can get by varying the duty cycle, we can get the variable output voltage at DC. So up to here we are clear. So when you take the switch, so the average for ideal switch, the average power loss equal to 0. For ideal switch, the average power loss is equal to 0. Average power loss equal to 0. When average power loss equal to 0, the input power is equal to the output power. The input power is equal to the output power. So if you take that, the efficiency in the switching network is 100%. 100%. Now you have to decide that in these three networks, which networks we need to choose. Let me tell you guys. So in these three networks, which network we need to choose? Let us take these three networks. So which network we need to choose? So efficiency is the major parameters. So which network we need to choose? Let me choose. So let me mark it as A, B, C. Let me mark it as A network, B network, and C network. So which network we need to choose to get the maximum efficiency? So whether it is resistive network, or so whether it is active mode operated transistor network, so transistor network, or when it is operating as a switch. Which network we need to choose to get the maximum efficiency? To get the maximum efficiency, which network we need to choose? So tell me guys. So waiting for your answer. So let the session will be the most interactive. You will get more concepts. So if it is interactive. So let us respond guys. So here three networks are there. First network is resistive network, and the second network is transistor operating in the active mode, and the third network is transistor acting as a switch. So to get the maximum efficiency of the power converter, because efficiency is the major parameter, so to get the maximum efficiency, we need to have the switching or the active mode operated or resistive load. So right, you are right. See, so because the efficiency is the major parameters. This is the reason. So this is the reason we are using the switches in the power converter network. So now you are clear, right? So we are using the switches in the network because switch having the average power loss equal to 0. If average power loss equal to 0, for ideal switch it will be 0. If it is 0 means the input power is output power, the efficiency will be 100%. Now let us go into the next slide. So here, so let us see the placement of switch. So one power electronic circuit is there. So I have given one power electronic circuit. So can we place switch at any place in the circuit? So for example, this circuit will be like this. Let the circuit will be like this. In this circuit, can we place switch at any place? Can I place here? So is there any basic rule? There are two basic rules. So we cannot place switch randomly. So we have some basic rules. Let me discuss the basic rules of the placement of switch. How we can place the switch. So here, so let me take, so the first point for the placement of switch, so to obey the KVL and KCL, the placement of switch should be, the unlike sources should not be connected. So the unlike sources should not be connected. So this is the basic rule we need to follow. The first rule here is for placing the switch, it should obey the KVL and KCL. So what is KVL and KCL here? So to obey the KVL and KCL, the unlike sources should not be connected. For example, it is voltage source. So the unlike sources should not be connected parallel. So the unlike sources should not be connected in the parallel. For example, if I take the DC source and AC source, can I connect both in parallel? So no. So similarly, so two unlike current sources cannot be connected in series. Two unlike voltage sources cannot be connected in parallel. Two unlike current sources cannot be connected in series. While placing the switch, so we should remind that. So this is the first point. So let us see in the simplest circuit manner. So will you answer or not? Let me check. So let me take two voltage sources. So the first circuit will be here. So it is a DC source. And the second, I will place the switch here. And the second source will be the AC source. Let me take the second source is AC source. So this is one circuit. Let it be the circuit 1. So now let me take the circuit 2. So I will take the current source. Here. So I will connect the one more current source. So both current source has the different magnitude. Let it be the I1. Let it be the I2. So I will place the switch here. So if you observe these two circuits, this switch should be always open or closed. In the first circuit, so tell me guys, be interactive so that you can understand the concept very clearly. For the placement of switch, so in the power electronics, the most difficult part is placing the switch. So where we have to place the switch to get the required output. If you understand here itself, you can understand in DC to DC converter very easily. So observe guys. So here first point is to obey the KVL and KCL. So the unlike sources should not be connected. Here I have drawn the two circuits. The first circuit will be the voltage sources. The second circuit is by the current sources. So I am asking the question that, so in the first circuit, the switch is in the open condition or closed condition. It should be always in the open condition or it should be always in the closed condition. So it's Thirumal, so it's wrong. It is not closed condition. It should be in the open condition. So Harsh, you are right. So it should be in the open condition, because if I close this switch, what happens? This DC source is connected to the AC source. So which does not obey the KVL and KCL, right? So this should be always in the open condition. So in the second circuit, the switch should be open condition or closed condition. So in the second circuit, the switch should be in the open condition or closed condition. Let us see the second circuit. Let us analyze the second circuit. So in the second circuit, the switch should be the open condition or closed condition. So the switch should be always in the closed condition. So here the switch should be always in the closed condition. If I open the switch, what happens? These two unlike current sources are connected in series. If I close the switch, what happens? So this current source will be deviate from this short circuit path. So here always in the closed circuit. So here always in the open. This switch should be always in the open. So if you understand this concept, so that is sufficient to apply. That is sufficient to placement of switch. That is the first point. Now let us discuss the second one. So the second point is energy sources should not be interrupted suddenly. Energy elements or energy sources should not be interrupted suddenly. So what is the second point, guys? The energy sources should not be energy elements. Let us take energy elements. So energy elements should not be interrupted suddenly. So what are all the energy elements? So let me take, so inductor and capacitance. Let me take inductor and capacitance are the energy elements. So inductor and capacitance. So what is the thing here? So here, when the circuit having the inductance and capacitance, we should follow some basic rule. So what is that? So the switch should not be connected in series with the inductance. So if you connect like this, so this circuit will not function as normal circuit. So why it is, you will see here. So now, so what is this? This circuit. So we cannot connect the switch in series with the inductance. So if I connect like this, what happens? If I connect like this, let it be the VL equal to LdI by dt. L di by dt. If I connect in series, if it is power electronic switch, it will operate at a high frequency. So with less time, it will be on and off. So this time will be less. Let me take it as a 0. So if the current is interrupted suddenly, so which causes more voltage induced in the high voltage induced in the inductance, so which causes damage of the switch as well as power electronic circuit. So that the switch should not be connected in series with the inductance. Directly we cannot connect in series with the inductance. So that is the first point. So the switch should not be connected in series with the inductance. So now we will see the capacitance. So how the capacitance can be? So let me take the capacitance here. So here, if I take the capacitance is energy element, so that we could not interrupt suddenly. So here, for the capacitance, the switch should not be connected in parallel with the capacitance. If the circuit is like this, so it will not function as a normal circuit. So we should not connect this circuit. So two basic rules. What are the two basic rules? The switch should not be connected in series with the inductance. The switch should not be connected in parallel with the capacitor. If I connect the switch in the parallel condition, so parallel with the switch, what happens? So observe here. So let it be the I equal to C into dV by dt. So within zero time, so if I close on and off the switch, what happens? Which causes interruption, which causes change in the voltage, so this value will be high. The more current will flow through the circuit, so which will damage the circuit. These are all the two fundamental rules. What are all those fundamental rules for placing the switch? The first rule here is, so here the circuit should obey the KVL and KCL. So for that, two unlike sources should not be connected. If it is voltage sources, they should not be connected in parallel. If it is current sources, two unlike current sources, they should not be connected in series. So on the next point is the energy sources or energy elements should not be interrupted suddenly. If it is inductor, we cannot connect the series switch. So if it is capacitance, so we should not connect the parallel switch. So these two circuits should be avoided for designing the switching networks. This is about the placement of switch. So up to here we are clear, guys. So if you have any doubt, you can ask. Right, Saha, you are right. So if you have any doubt, you can ask. So up to here we are clear. Let me go forward. So if you have any doubt, you can ask. So if you have any doubt, you can ask. Right, clear. So now let us see. So what is the difference between the ideal switch and practical switch? Let us see what is the difference between the ideal switch and practical switch. So now let me take the ideal switch here. So ideal switch and practical switch. So let us understand both at same time so that you can understand when you compare both of them. So let me take a switch here. Let me represent with the other color. So let me take a switch here. Let VSW is the voltage across switch. VSW is the voltage across switch. ISW is current flowing through the switch. Let VSW is the voltage across switch, ISW is the current flowing through the switch. So any switch if you take, so there are only two possible conditions, 1 and 0. One is on condition, other one is the off condition. So there are only two possible conditions. So one is on condition, other one is the off condition. So on condition is also called as conduction mode. Off condition is also called as blocking mode. Blocking mode. So there are two modes. So one is conduction mode, other one is the blocking mode. A switch has only two states, right? So when it is in on condition, so for ideal switch, first we will see for the ideal switch. So after that we will go for the practical switch. Now, So when it is an on condition, now let us analyze for the on condition. So let the switch is in the on condition. So what is the current flowing through the ideal switch? So the switch current is equal to the I on, let it be the I on state current. The switch current is equal to on state current. This on state current has no limitation. This on state current has no limitation in case of ideal switch. So what does it mean? So if you take the practical switch, there is some limitation for every current. There is some limitation for the current flowing through the switch, current capability of the switch. But so if you observe here, so for an ideal switch, if you take an ideal switch, there is no limitation. That is minus infinity to infinity. So the current can flow. So it can allow from the 0 to infinity. Let me take the 0 to infinity. So ISW. Let me take the 0 to infinity. So here the ISW, that on state current, has no limitation in case of the on condition of the switch. So let me take the practical switch. The same parameters let us analyze for the practical switch. So what about the practical switch? Guys? So now for the practical switch, let us analyze for the practical switch. So for the on state of the practical switch, so what happens? So in the practical switch, the ISW is I on. Again, the current will be flowing. When switch is in closed condition, the current flowing to the switch. So but there is some limitation for the practical switch. So which is, it has the limitation in between the I minimum to I maximum. So the I on should be in between the I minimum to I maximum. So in ideal switch, there is no limitation. So in ideal switch, there is no limitation. So in practical switch, there is a limitation for the current. Now let us see on state resistance. For ideal switch, when switch is in closed condition, the on state resistance equal to 0. So similarly, so for the practical switch, on state resistance is not equal to 0. Because it's a practical switch, it has some on state resistance. So on state resistance is 0 here, on state resistance is not equal to 0 in the practical switch. Now let us take voltage across switch during on condition. So during on condition, so what is the voltage across switch? Because it is in the on condition, the on state resistance is 0. So if the current is flowing, so I switch on into R on equal to 0, so which will get the 0 voltage. So V switch equal to, so V on, let it be the V on voltage during on condition. So here, which is equal to I is on, that is current flowing through the on condition, into R on. So what happens? So in the ideal switch, the R on value equal to 0, so that voltage across switch is also equal to 0. So if you compare with the practical switch, when I close the practical switch, there is an on state resistance. If the current flowing through the on state resistance, what happens if the current flowing through the on state resistance? So there is some voltage drop, so that V switch, which is equal to V on, should not be equal to 0. So in practical switch, it is not equal to 0. So now let us see the off state conditions also. For the same ideal switch. Now we have seen the on state conditions. Let us see the off state condition for the ideal and practical switch. So for ideal switch, when switch is in off condition, so that is in blocking mode, when switch is in off condition, so what happens? Let us analyze for the ideal switch as well as practical switch. Both we will analyze. So what happens here? So for the ideal switch, so when switch is in off condition, so what about the current? I switch equal to, I off equal to, when switch is in off condition, it has the infinite off state resistance, so that the current flowing through the switch equal to 0. So for example, so let me take the current here. Now we have taken the current. Similarly, off state resistance. What about off state resistance? The off state resistance equal to, So offset resistance equal to infinite, because it is in the open condition. When the switch is in open condition, so it offers an infinite resistance for ideal switch. So here, so R offset resistance equal to infinite. So R off equal to infinite. Similarly, let us see the ISW here. In a practical switch, the current flowing to the switch equal to, so which is not equal to 0. So when it is in open condition, there is some leakage current flowing to the switch, so that which is not equal to 0. During off condition in practical switch. In practical switch, there will be some current flowing through the switch. Through the switch, unlike the ideal switch. Because, so the offset resistance is infinite here. So because there exists a offset resistance, so here there will be some offset resistance available in the practical switch. Now, let us see the voltage across switch. So voltage across switch during off condition, so which has the, so we can block, so it is a blocking mode, which can block infinite voltage. That is, it can block minus infinity to V of, so infinity. There is no limit for the blocking voltage for the ideal switch, but in a practical switch, so there is a limitation for the blocking voltage also. So when switch is in off condition, so what happens? When switch is in off condition, so there is a limitation for the, so V off, So V off in between the V minimum to V maximum. So there is some constraint for the V off in between the V minimum to V maximum. So these are all the basic parameters for the on and off of the switch. So we have seen the current flowing through the switch, and we have seen the, so on-state resistance and off-state resistance of the switch, and we have seen the voltage across switch. Let us draw the, so these properties into graph. So now, first I will take the ideal switch. So how I can draw, we'll see here. Let me take the VSW here. VSW is nothing but voltage across switch. Let the switch is off for this instant. Let the switch is off for up to here. Let the switch is in off condition. Let us assume. And from here to here, let the switch is in on condition. So from here to here, again, let the switch is in the off condition. Now let us draw. So VSW, that is voltage across switch. For the off condition, on condition, and off condition. So we need to draw the voltage across the switch. VSW. So when the switch is in off condition, there will be some voltage. It depends on circuit how much voltage it has. So let it be the V off. So we have the V off voltage across the switch. Because for an ideal switch, it can block the infinite voltage. It can block the up to infinite voltage, but how much it has to block, it depends on the circuit. So it will be the V off. So at on condition, what happens? When switch is in on condition, the on-state resistance equal to 0, so that voltage across switch equal to 0. Again, when it is in off condition, so again it exhibits, it has some voltage across the switch. So this is voltage across the switch for the ideal switch. Let me draw the current also. Flowing through the switch. How I can draw the current flowing through the switch? When off condition, during off condition, what is the value of the current here? So during off condition, the current flowing through the switch equal to 0. So from up to here, so because it is in off condition, the current flowing through the switch equal to 0. So during on condition of the switch, what happens during on condition of the switch? During on condition of the switch, there will be some current. So and how much current it will flow, it depends on the circuit. So let me call it as a I on. So the I on current will flow through the switch. Because when switch is in on condition, the current flowing through the switch. Again, when the switch is in off condition, the switch is in off condition, the current flowing through the switch. Now let me draw the power. So which is equal to VSW into ISW. We need to multiply these two waveforms. When I multiply during off condition from here to here, so there is some voltage across the switch during off condition, but the current is 0 here. Now, so if I multiply both of these, what happens? Something into 0 equal to 0, so that power equal to 0. So during on condition, voltage across switch is equal to 0, current flowing through the switch, current is flowing through the switch. So that when you multiply both of these, what happens? Again power will be 0. Power will be 0. Again here if I multiply, the power will be 0. So from that what we can observe here, so the average power in the ideal switch is equal to 0. The average power dissipation for the ideal switch is equal to 0. Now let us draw for the practical switch. Now let us draw for the practical switch. So now let me draw for the ISW. Let me draw for the VSW, voltage across switch. So here, so how we can draw the voltage across the switch? Again, here also I will mark the off state. So from here to here off. Again, so let me take this period as on period. Again, let me take this period as off period. Now let me draw the voltage across the switch. So how we can draw the voltage across the switch? So during off condition, initially let it be the V off. So from here to here it will be the V off. Let it be the V off. So during off condition it has the V off voltage. So here if you observe here, at this instant you need to observe here, you need to concentrate here. So at this instant what is happening? So the switch is changing from the off state to the on state, If you observe here, so there is immediate transition from the off state to on state. But in a practical switch, there is no immediate transition. There is some delay from the off state to the on state. So when it is an on state, what happens in a practical switch? During on state, in an ideal switch, the voltage will be 0. But in a practical switch, there will be some voltage appears across the switch. So that voltage will be the V on. So from here to here, it will be the V on. So now we have the V on here. So now at this instant, what we are doing? Observe here. At this instant, what we have done? So from on state to the switch has to change from the on state to the off state. To change from the on state to the off state, so there is some delay will exhibit. They exhibit in the practical switch. So in the practical switch, so it will be like this. So what is this? If you observe here, so from off state to on state, there is some delay. That is turn on delay. We can call it as a turn on delay. So similarly, so here from on state to, this is the on state, right? Up to here it is in the on state. So to change from the on state to off state, there is some delay. There is some more delay. So which is the T off. So which is the turn off delay. So this is the voltage across the switch. If you can understand the ideal switch, and if you can get the parameters, you can easily draw. So now let us draw the ISW. So current flowing to the switch. How we can draw the current flowing to the switch? Observe here. So during off condition, from here to here the switch is in the off condition. During off condition, what happens? So during off condition of the switch, the current flowing to the switch, ideal switch equals 0. But in case of practical switch, is it 0? So no, because during off condition also in a practical switch, there is small leakage current in terms of microamperes it flows. So that let me represent that small current value here. So which is the off state current. Let me call it as a I off. The current flowing to the switch during off condition. Let it be the I off. Now it has to change from off state to on state. So from up to here. So after this instant, so it has to change from on state to on state. So off state to on state. So it has some delay which is called as turn on delay. So when it is in on condition, there is some current flowing to the switch. So which is equal to I on. Current. So again at this instant what happens? The switch has to transition it has to take the transition from the on state to the off state. At this instant it has to take the transition from the on state to the off state, so that it exhibits some delay. So which is like this. So let me mark this as. Now let us draw the power. For this circuit. Now let me draw the power flow across the switch, power dissipation of the switch. So let me draw by using the instantaneous powers. So here V off into I off. Here, so voltage across switch into current flowing through the switch is equal to power, PSW. Now let us multiply these two waveforms. So what happens during block state, during off state of the switch, there is some voltage across the switch and there is some small current flowing through the switch, so that the power will be like this. The power will be like this. If you multiply both of this, the power will be like this. So after this, so what happens? So this is decreasing in nature and this is increasing in nature. So if I multiply both the things, so I will get the waveform like this. So after this, again during on state, so from here to here, if you observe, so there is on state current and there is on state voltage. If you multiply both of them, so what happens? So there will be some losses here. So again during turn off time, so it will be like this. So let this will be the T on, so which is called as turn on delay, so which is nothing but, so from off state to on state, how much time taking it is. So from transition from the, so the switch transition from the off state to on state, so off state to on state, which is called as turn on delay, let me represent with the T on. So here during T off, so it will be like this. So here, so these PSW is the, for representing losses, these total losses are divided into two types. One is conduction losses, other one is the switching losses. Now, these two are the conduction losses. Let me represent with the other color. So these two losses are from here to here. So from here to here, these losses are conduction losses. So which are conduction losses. And if you observe these two, let me represent with other color. So if you observe these two are called as the switching losses. During T on and T off times, whatever be the losses induced in the switch, so they are called as switching losses. So the operating speed of the device, will depends on these transitions, that is turn on transition and turn off transition. So this, let us compare that also. So up to here we are clear, right? If you have any doubt, you can ask. So up to here we are clear. Arun Kumar, yes, I will post in the Telegram group. So from today onwards, these lectures I will post in the Telegram group. So up to here, you are clear or not? So we have drawn the characteristics for the ideal and the practical switch. So from the basic parameters, so we have found that there is a switching losses and conduction losses exist in case of practical switch. So now let us compare that also. So let us compare the operating speed. How the operating speed will be? So the operating speed is more in case of ideal switch. So why the operating speed is more in case of ideal switch? Because there is no turn on transition and turn off transition in case of ideal switch. The operating speed is high because, so the turn on and turn off transitions are 0. So here the T on and T off are the 0. So that is turn on transient and turn off transient are 0. Transitions are 0. So that the operating speed is more. So if you observe in the practical switch, there is a finite turn on time. and turn off time. So if you find the switching frequency, so it will be the 1 by T on plus T off. So the switching frequency equal to 1 by T on plus T off. If the turn on and turn off transients are low, transitions are low, so what happens? If these transitions are low, the switching frequency is more. The device will operate with the more speed. So this is about operating speed. So if it is having the more frequency, so the operating speed will be more. When compared to the ideal switch, the operating speed is less. So here in ideal switch, there exists a conduction loss and switching losses. So here the conduction losses and switching losses are 0 because average power dissipation is equal to 0. Conduction loss equal to 0 and switching loss also 0. switching loss also 0. Switching losses also 0. Conduction loss and switching loss are 0. Here the conduction loss and switching losses will exist, which is not equal to 0. Conduction losses and switching losses are not equal to 0. Switching losses are not equal to 0. So this is about ideal switch and practical switch. This is about ideal switch and practical switch. So now, so let us see how to find the switching losses for the practical switch. How to find the switching losses for the practical switch. Let us see. So we have drawn the characteristics. Up to here we are clear, right? So if you are clear, let us go into the so if you are clear, let us go into the session. If you are clear, let us go into the next slide. So let us start the analysis. If you have any doubt, you can ask, guys. If you have any doubt, you can ask. So up to here, if you have any doubt, so in the need of the switching, so placement of the switching and ideal switch and practical switch properties. So in this, if you have any doubt, you can ask. You can raise. If you have any doubt, you can ask. So Yashaswini, in case of practical case, what happens if I on and V off does not maintain limit? So if it does not maintain limit, if it is cross the limit, so the rating of the switch, if it is cross the rating of the switch will fail. If the device will damage, the device will damage. If it is applying more current, so more current, there will be the hotspots will be developed, so which will damage the device. Now let us analyze the practical switch. Now let us analyze the practical switch. Now let me mark the different period for this. So we know that from here to here the switch is in the off condition. So let this white color is voltage across switch. So let this yellow color is current flowing through the switch. So let this white color graph is voltage across switch. During off condition, there exhibits some voltage which is V off. Let me mark the V off here. So let me mark V off. During off condition, from here to here, during off condition. So this period is called as T on. This period is T on. And from here to here, so the current is again V off. This period will be the V on. That we have already done. I am representing here, that's it. So it will be the V off. So it will be the graph will be the with respect to time we are drawing. So now so let me mark for the current also. So during off condition, the current will be the I off. During off condition, let the current flowing to the switch is equal to I off. During on condition, the current will be the I on. Let the current is I on. Again during off condition, the current will be the I off. So let me take the period from here. So from here, let me start from here. So from here to here, on condition and off condition. So let it be the total time of the switch. So total time of the switch. That is on time and the total on time and total off time of the switch is let it be the total time TS. Let me represent with the T off. So on this off transition, let me represent with the T off. So this is the graph we have drawn in the practical switch. Now, so to analyze the practical switch, we need to take some assumption. So what are all those assumptions? The assumptions are I off equal to 0. So that is, so during off state, so the current flowing to the switch, we are assuming that is 0 because it is a leakage current. So it is in terms of microamperes. So that we are assuming that this will be 0. So and the second assumption is voltage across the switch during on condition equal to 0. Now, so let me modify this graph. By making the voltage across switch is equal to 0. So I need to shift this axis to the x-axis because I need to make this V on as 0. And here I need to make the I of as 0. Now let me draw the by using the assumptions. Let me draw the, so here voltage across switch and current flowing through the switch. Let me take voltage across switch. So voltage across switch VSW. So here it will be the V off. Right? So So V on equal to 0, V on equal to 0. So from here to here it will be the T on. So from here to here it will be the T off. From here to here it will be the T off. So next we need to take the D into TS. So here it will be the total time. So from here to here it will be the total time TS. Total switching time, that is both for on and off, both for on and off. So during on condition, so at this instant we are turning on the switch. So up to here, so it will be the D into TS, that is on time of the switch. D into TS, that is duty cycle into time period, which is on time of the switch. So and the remaining period is the off time of the switch. So now, so it is V off and it is I on, it is I on, it is I on. So now let us find, so switching power losses. Let us find the switching power losses from this graph. How we can find? Let us see. Switching power losses we need to find. Switching power losses we need to find. Let us find the switching power losses. Let us find the switching power losses. For this graph, we need to find the switching power losses. So now let us analyze this graph and find the switching power losses. The switching power losses are, so the switching power losses PSW equal to, the switching power loss equal to, so let me take the two different periods, switching losses for the on-time period, on-time transition, switching losses for the off-time transition. So PSW on, so that is during on-time transition, so PSW off, so plus, so the power losses, the switching losses during off-time, during the off transition. How we can find, we will see. So during the T on period, so let me find the voltage and current. So here, so VSW during the time period of 0 to T less than T on, so 0 to T less than T on, from here to here, let me find the voltage across switch and current flowing to the switch. So what is the voltage across switch? So voltage across switch equal to, so what is the voltage across switch? So if you observe this here, so from here to here, this is the downslope line, So if you apply the line equation, that is y equal to mx plus c, the slope is negative, and the C value here, it will be the V of, C value will be the V of here, right? C value here, it will be the V of, and the slope is negative. So how the slope can be calculated? It will be the V of into minus V of into T by T on. So the slope, the C value will be the V of. So it is a simple line equation, that is y equal to mx plus c. So we need to consider for the period of 0 to t on. So understand guys, in between the 0 to t on, we need to consider. So to find the switching losses, because the switching losses occurs at, so turn on transition and turn off transition. So now this is the voltage across the switch. So here, let me represent here. So which is equal to V of into 1 minus T by T on. So during on transition, so the voltage will be the downslope. So the current will be the upslope. So how I can find the current expression? So this is also line equation. How I can write the line equation? Y equal to mx. Because it is starting from, let us assume that because it is starting from 0. So assume that this is a y equal to mx. So y equal to mx for the current. So for the current, it will be the y equal to mx. So m into x. So x is the time period. So slope will be the v of divided by t on. So ISW. Let me find the ISW during on condition. So ISW during on condition, it will be the, during on transition, it will be the I on into, this value is I on, right? This value is I on. So I on into T by T on. Now let us find the switching losses. So now let us find the, so from here also let us find remaining things also, 0 to T less than T off. During the off transition, let us find during the off transition. During this period, let us find VSW and ISW. So here the current is the downslope, so voltage has the upslope. If it is downslope, we need to multiply with the 1 minus T by T on. So if it is upslope, we need to multiply with the T by T on. So here, now let us write the expression for the T off by T on. So here, during turn off time of the switch, what happens? So voltage across switch equal to, So it has the, so voltage across switch will be the white line, this line. So it will be the V off into T by T off. V off into, so here we need to consider the period of the T by T off, right? Similarly, find the current flowing through the switch. How the current flowing through the switch can be found? So ISW equal to, so the current is yellow color during turn off transition. So what happens? It has the downslope. It is simple line equation, y equal to mx plus c. It has the downslope. So which is equal to I on into 1 minus T by T off. 1 minus T by T off. Now we have find, so during on condition, voltage across switch and current flowing through the switch. During off transition, so voltage across the switch and current across the switch. Now we need to find switching losses. So let me find the switching losses. By using these two expressions, let me find the switching losses. Now let me find the switching losses during the turn on transition. So switching losses for the turn on transition. How I can find? So PSW on, that is switching losses during on transition. So switching losses during the on transition, how I can find? I need to take in between the 0 to T on, 0 to T to T on. So I need to take the total time period 1 by Ts into integration of 0 to Tn. What is the period I need to consider during the turn on? I need to consider period of the 0 to Tn. I need to multiply with the VSW into ISW. So VSW value will be the V off into 1 minus T by T on. So into I on into T by T on. Into dt. Now let us integrate this one. So let us integrate this one. To find the on-state switching losses. If I find to find the on-state switching losses, it will be the 1 by Ts. So integration will be the, if V off and I on are the constant values, let me bring it outside, V off into I on. So integration of 0 to T on. If I multiply both of these, it will be the T by T on minus T square by T on square. Into dt. So for this we need to find the integration. So how we can find the integration? So here let me find the integration also. 1 by Ts into V off into I on. So here if I apply the integration for this first term, that is T by Tn, what is the value I will get? T square by 2 into T on minus T cube by 3 into T on square. So apply the limits as 0 to T on. So if I apply the limits of 0 to T on, so what is the value I will get? So I will get the, so V off into I on divided by Ts, into, so if I take this one, I will get the T on by 6. So this is the expression for the PSW on. So that is switching losses during the on transition. Now let us find switching losses during the off transition. Now let us find switching losses during the off transition. Now let me find. So how I can find the switching losses during the off transition? So PSW off, I need to find the PSW off. So that is switching losses during the off transition. So which is equal to 1 by Ts, integration of 0 to T off we need to consider. So what is the value here? So we need to multiply with the VSW into ISW. So VSW into ISW into dt. So now if I multiply this one, so where these values come? So where are these values? So we have already derived these values. So 0 to, in between the 0 to T off, so VSW equal to V off into T by T off, right? So ISW equal to I on into 1 minus T by T off. Let us multiply both of that. So both of these. let us multiply so both the things. So now let me multiply both. So I will get the 1 by Ts into, so which will be the 1 by Ts into integration of 0 to T of VSW value will be the V of into T by T of and ISW value will be the I on into 1 minus T by T of into dt. So into dt. So this one we need to find. So how we can find? So V of into so I on divided by Ts. So integration of we need to find the integration of 0 to T of so what is the value we need to find? T by T of into 1 minus T by T of into dt. So we need to find this one. How we can find? So if I find these losses, this is similar to this one. So these both are similar. If you observe, this is also integration of T by T on, integration of 1 minus T by T on into T by T on. So this is also same, but here T off will be there, here T on is there. So in both the derivations are same. So if you observe, the integration of both the derivations are same. So the only difference is here T on is there, here T off is there. So if I apply the integration, I will get the value as V off into I on divided by Ts into T off by 6. So this is the losses during the off condition. So now we have the losses in the on condition as well as off condition. Let us write the final expression for the switching losses. So the switching losses equal to PSW. Let it be the PSW. So which is the summation of the on-time losses as well as off-time losses. So which is equal to V off into I on divided by Ts into 6 into T on plus T off. So this is the expression for the switching losses. So now let us find the maximum power. What is the maximum power we need to find? So if you observe here, so what is the maximum power? Let us find the maximum power. So what is maximum power? Let me clear what is maximum power. So in this if I find the power loss, so maximum power is nothing but we need to find the maximum power. So in some of the problems they are asking about the maximum power also. So what is the maximum power we need to find? If you observe here, so from here to here we can call it as the maximum power. So Pmax, this Pmax we need to find. So at which the maximum value occurs and the magnitude of the maximum value we need to find. How we can find? Let us see. So during on condition, so the maximum power, let me find the maximum power expression. Maximum switching power. So maximum switching power. During switching, so what is the maximum power? Apply maximum power loss of the switch. So now let me find the maximum power. To find the maximum power, I will take the limits in between the 0 to T on. 0 less than T less than T on. So in between the 0 to T less than T1, I need to find the power and I need to make the derivative with respect to 0. So how I can find the power? So the VSW will be, during on condition, VSW will be V off into 1 minus T by T on, right? 1 minus T by T on, this we have derived. So ISW equal to I on into T by T on, So we need to multiply both, and we need to find the derivative. So after that we need to make it 0 to find the maximum value. So now let me find the maximum value. So here, let me find the maximum value. To find the maximum power. So I need to multiply both of them. So voltage across switch, I need to find the power, I need to multiply the voltage across switch and current flowing through the switch. So let me multiply. So the power equal to, first let me find the power. instantaneous power. So which is equal to V of into 1 minus T by T on 1 minus T by T on V of into 1 minus T by T on into I on into T by T on. So I need to multiply both. So after that I need to apply the derivative. So dP by dt equal to 0. I need to find the dP by dt. So V of and I on are the constant. Let me take outside. So remaining terms are T by T on. So d by dt of T by T on. If I multiply with both of these quantities, T by T on minus T square by T on square. If I apply the derivative, what happens? So it will be the 1 by T on, which should be equal to 0. So 1 by T on minus 2T by T on 2T by T on square, so equal to 0. So 1 by T on, so minus 2T by T on square equal to 0. So from that, so 1 by T on equal to 2T by T on square. So from this, so T on and T on will get cancelled out. T equal to T on by 2. So where the maximum power occurs? If the question asking for, so where will be the maximum power occurs in case of switching losses? So which is equal to T on by 2. So if I substitute T on by 2, so in this expression, so if I substitute T on by 2 in this expression, I will get the maximum power. So let me substitute T on by 2. So this is the expression for to get the maximum power. This is the condition. So to get the maximum power instant, this is the condition. At T on by 2, we will get the maximum power. Now to get the maximum power, let me substitute this maximum time. This time instant in the instantaneous power. Now let me find that. So here, if I substitute in this power expression, I will get the expression for the maximum power. So P max equal to so V of into I on. So V of into I on into, so in place of T, I need to substitute the T on by 2. So if I substitute T on by 2 here, it will be the 1 by 2. It will becomes 1 minus, in place of T, if I substitute the T on, what happens? T on by 2, so it will becomes 1 by 2. 1 minus 1 by 2 is 1 by 2. If I substitute in place of T, if I substitute the T on by 2, I will get the 1 more 1 by 2 here. So the maximum power will be V of into I on divided by 4. So the maximum power will be V of into I on divided by 4. So this is the expression for maximum power. So in this session up to here, we have seen the analysis of practical switch. So when we solve the problems, you can understand that how these switching losses can be calculated. So in the next session, we will see the types of switches as well as numerical problems. So up to here we are clear, right? So you are clear or not? Up to here you are clear or not? So we have find the need of switching, practical switch, placement of switching. So differences between the ideal and practical switch. So we have analyzed the practical switch also. So in practical switch we have found that switching losses as well as maximum power. Switching losses as well as maximum power. So up to here we have seen the switching concepts. In the next session, so we will see the types of switches as well as numerical problems. So thanks for coming to the lecture. So do subscribe to channel. So thank you very much.